All right, good afternoon. We're waiting a couple of minutes to start. Apparently there's a lot of road construction in Tempe. We have a group of people that are going to be showing up in person, and they might have been delayed, but I guess we might as well. We've got enough people on to go ahead and start. So this is our first afternoon technology learning series. This is going to be on finite element quality checks and model validity checks using MSc Nastran. This presentation is set up to be a little bit more like a reference rather than an overview PowerPoint. So you can take this PowerPoint here and basically build off of it for yourself as you're working. Take this as a starting reference and then begin adding all your own components with it. So with that, I'll give you the presenter, Austin Pizzella, and he'll start it off.
All right. So finite element analysis, or FEA, gives us engineers the ability to solve engineering problems that we couldn't do with pen and paper alone. However, the FEM must both properly model the expected behavior of the structure as well as be mathematically accurate. And so the purpose of this seminar is to give a little bit of an overview on some of the checks that should be performed to ensure that your model is mathematically accurate.
Whoa.
Is that?
Is everyone dialed in?
Should be.
Hit the little chat. You can turn on the little chat one.
No.
Whoa. You might have to redo it all.
Yeah.
Oh, sorry.
Technical difficulty.
All right. Click on the little phone so people see.
Can they see that?
There you go.
Yeah, I still see your screen.
All right. Just leave the phone number up for a second so
Okay.
people can.
So people will see that right there?
So there'll be a little pause while give people a chance to dial in. So you've got screen and dial in, right, John?
Yeah, I dialed in. I didn't use the internet, and I do have screen. I haven't seen it moving in a little bit, so.
Yeah, he's not doing anything right now.
Okay.
Go ahead and
Back
pop
to
up
the.
with- And just let me know if you see this popping up.
Yep.
Okay.
This is Pat Barnhill. I got the same thing John has.
Thanks, Pat.
You guys hear me? This is Eric.
Yes, we do.
Okay, I just joined by phone, so I think I'm set up now.
Okay, no problem.
Okay. Might as well go for it.
Just go for it.
Yeah.
Okay, here we go again. Finite element analysis, or FEA, gives engineers the ability to solve engineering problems that we couldn't do otherwise with simply pen and paper. However, the finite element model must both properly model the intended behavior of the structure as well as be mathematically accurate. So our goal in this seminar is to guide analysts on some of the checks that should be performed to ensure that the model yields mathematically accurate results. And also having a standard checklist within a company is a good business practice because it ensures consistency between both multiple analysts and as well as multiple departments. So it's important to note that even if a model passes all the checks that are presented here today, that you could still inaccurately model the intended behavior through modeling mistakes such as incorrect units, wrong material properties, or oversimplification of the problem. We also assume that all of the viewers have a understanding of FEA theory and a basic knowledge of MSc Patran and Nastran. So the first topic we're going to cover is element quality. So what is proper quality and density of a mesh, are essential to obtaining accurate results. However, if you ask different analysts what proper element density is, you're probably going to get a whole lot of different answers. However, the quality of elements is easily quantifiable using different metrics that are available in preprocessors such as Patran, or in solvers such as MSc Nastran. In Nastran, the elements are automatically checked and will alert the analyst of poor elements in the model and even terminate the run if elements are extremely poor in quality. So why do we care about element quality? Well, first and foremost, it affects the accuracy of the desired results that we're looking for, such as how accurate are the results away from the sampled integration points within the element. And it affects the condition of the global stiffness matrix, which subsequently affects runtime and round-off errors within the calculations. So both MSc Patran and MSc Nastran offer a variety of different element metrics to inspect the quality of the elements in the mesh. A few of the basic tests are covered here, and there is a table that can be found in MSc's Quick Reference Guide, or QRG, on pages 129 and through 132. So the first check is aspect ratio, which is simply the ratio of the longest side to the shortest side of an element, with an ideal value of 1. And there you see ideal elements for both triangular elements as well as quadrilateral elements, and skewed elements with aspect ratios of roughly 10. So MSc Nastran has a default for solid elements of an aspect ratio of 100. Angle deviation, or skew, is the next element quality check we're going to cover, which is simply the smallest angle between any of the 3 vertices for triangular elements, or the angle formed from drawing lines connecting the midpoints of a quadrilateral element. For quadrilateral elements, the default tolerance in Nastran is 30 degrees, while an ideal value for quads is 90 degrees, which would be a perfect square. For triangular elements, your ideal value would be 60, which would make it an equilateral triangle with an MSc Nastran default of 10 degrees. Perhaps the most comprehensive element check is the integration point Jacobian determinant. And this is performed at where the determinant of the Jacobian is calculated. A well-formed element will have a positive determinant of Jacobian at each integration point and won't have a lot of variation between the different integration points within the element. And the minimum Jacobian determinant is reported by the solver. So ideally you want a determinant that is positive, greater than 0, and an Nastran default tolerance is set to 0. And this same check is referred to in Patran as the Jacobian 0. So MSc Nastran gives the analyst the ability to change the tolerances for the checks that are run from the default tolerance using the geom check card in the executive control portion of the analysis deck. For example, if you wanted to change the skew tolerance for quadrilateral elements, you would use geom check Q4 underscore skew equals 15 if you wanted to change it to 15 degrees. And pages 30 and 31 in the QRG have a table of all the element tests and default tolerances that are used by Nastran. Also, the tolerances can be changed within MSc Patran for the tests that are performed in Patran by using the utilities change verification parameters, which can be found under utilities and then going to FEM general. So element quality checks in Patran can be found by clicking the meshing tab and then changing the action to verify. Both fringe plots and tabular data are available in Patran, and there's quite a few tests in Patran that are not available in Nastran, just for more viewing potential for the analyst, more metrics. Fringe plots can be seen by going to verify and then changing the object from element to either triad, quads, tets, whatever specific element type you are interested in. You can also view the tabular data by just changing from the element type, and then under test you select all. So at times, software meshers can produce erroneous elements. For example, in Patran, if you're trying to seed a solid mesh with a shell mesh on one of the surfaces, it's possible for the mesher to create some highly degenerate elements. For example, I included two pictures. The one on the left shows two elements that look to have decent element quality. However, when you rotate the view, you see that they're almost perfectly flat. It's hard to avoid this sometimes, and you need to ensure that these elements aren't created when you are doing techniques such as seeding the solid mesh with a 2D mesh. So if you do get these elements and you notice them, you can either remesh your surface or solid, or you can try to use the tool in Patran by going to Modify Mesh and selecting either solid or shell as the type. And essentially the software has algorithms that will try to improve the mesh quality based on different parameters, such as for solid elements you can choose to improve the mesh based on the collapse ratio or the Jacobian minimum, or both. And while the checks in the preprocessor are extremely helpful in identifying poor element quality before you start solving the model, you should always ensure that your model checks the MSE Nastran default tolerances before you are handing off the model to another analyst or submitting the model to a client. And I included a useful method for finding and highlighting elements that failed MSE Nastran checks in the FO6 at the end of this presentation. So the next topic is model validity checks. So below is just a quick summary of some of the tests that should be performed in each of the Nastran solution types. So if you're building a model in Solution 101 and time and budget are an issue, you might not necessarily be interested in checking the model in Solution 103, but it is recommended if you have the time and money to do so. So checks within Solution 103, which is normal modes, you want to run the model as free, and you want to check the rigid body modes of the model, as well as the grounding checks and element quality checks, which are turned on by default. In Solution 101, which is linear static, you want to run 1G inertial loads in the X, Y, and Z directions, and force displacements, which are run separately from 1G. And in these runs, you want to check the epsilon, which is the round-off error, the excessive pivot ratio, and ensure that your elements are passing the element quality checks. So in Solution 103, free modal, you want to ensure that your model behaves as a rigid body, just like any real-world object would. And to do this, you want to run the model unconstrained, so no SPCs defined at any mounting locations or fixities. And you want to request at least the first 7 modes. You want to use the IGRL card in Nastran, or you can simply select Solution 103 when writing out your analysis deck out of Patran. For example, the IGRL card I provided here is simply asking for the first 20 modes between 0 and 2000 hertz. So the criteria you want to meet here, you want to see the first 6 modal frequencies of the model have near 0 frequencies and correspond to the first 6 degrees of freedom of the overall model. So regardless of element type used, any properly built model should have 6 rigid body modes. The first 6 reported frequencies should be roughly 10,000 times smaller than the first natural frequency of the model, which is mode 7. And we requested the first 7 modes so that we get to actually see that first modal frequency. If you have different components that aren't connected properly, you'll actually see below zero frequencies for even the first 10 or so, depending on how many different bodies you have moving. And rigid body frequencies that are small but not extremely small are likely indicative of modeling issues. And it's also important to realize that these frequencies are associated only with the rigid body modes and do not have any real-world meaning. They're simply assigned to them by the solver. So when running Solution 103 free, you also want to run ground check. Nastran's grounding checks are intended to check the rigid body strain energy of the model at different level sets as the model is being reduced. And I'll describe these sets on the following slide. And essentially, we're verifying that the model behaves as a rigid body and has no or near zero strain energy due to unintended constraints. So you want to use the ground check card in the case control, and it's recommended that you use set equals all and data rec equals yes. So as we said previously, you want to run the model unconstrained in Solution 103 and ask for at least the first 6 modes, but 7 are recommended because you're also looking for those first 6 rigid body modes. So near zero values for strain energy are desired, and also Nastran will give you a nice pass or fail for each of the 6 degrees of freedom. The tolerance for pass or fail is determined by dividing the largest stiffness term in the stiffness matrix divided by 1e to the 10, which is changeable by the analyst. Data rec, or data recovery, is set to no by default, but using yes will help guide you to the problem areas if you are failing in different sets. Failure in one set will result in failure of all the following sets as well. And it's important to remember that you want to run the model unconstrained, both to see those rigid body modes as well as passing in the F and A sets, which will fail if you do constrain the model. So on this slide, I'm just defining the sets that we want to check. There are 5 in total, and the strain energies are reported for all 6 degrees of freedom for the requested sets. So the first set, G set, is the entire model before the solver applies SPCs, NPCs, and RBEs. Next, the N set is the G set with NPCs and RBEs applied, and if you have auto SPC set to yes, which it is by default, or if you are using auto SPC equals no and you have unconstrained degrees of freedom, you'll see N set plus auto SPC, which is all the degrees of freedom that are being constrained once auto SPC is being applied. Next is the F set, which is the entire model after SPCs, NPCs, and RBEs are applied, as well as those degrees of freedom constrained by auto SPC, if applicable. And finally, you have the A set, which is the analysis set using the eigen solution. And I've also provided a quick picture of the sample of the G set test, and we see that it's testing it in all 6 degrees of freedom and lists the strain energy for all 6 and gives us a nice pass at the last column there. So along with using data recovery equals yes, the set in which the failure occurs helps guide the analyst to where problems are occurring. And as I mentioned previously, if you constrain the model in the if you constrain the model, you're going to fail both the F set and the A set. And for example, if you have failures in the G set, all your subsequent sets are going to have failures in the same degrees of freedom as well. Some possible examples of where you are seeing failures in the G set could be coordinate coupling. If you have an RBE with slave nodes in different coordinate systems, highly degenerate elements, CLAS elements with non-coincident nodes, or ill conditioning in the matrix, possibly due to short beams. Failures in the F set could be due to incorrect definition of NPCs. Failures in the F set could be over-constrained due to SPCs, And finally, failures in the A set could be either due to overconstraints due to the SPCs. The grid used by default in ground check needs to be specified because it is too far away from the center of gravity of the model, or auto SPC is activated and is constraining near singular degrees of freedom. Also, it's important to note that since these checks are performed as the model is being reduced by the solver, the user can actually watch the FO6 update, and you can actually see these tests being performed as it reaches each of these sets. So you don't have to wait 3-4 hours for your model to completely solve to see if you're going to fail the grounding checks, which is extremely useful when you have large models. So next we have solution 101 checks. That first test you want to run is the 1G inertial loads, and you want to apply a 1G inertial load in the X, Y, and Z directions, and this can help reveal modeling issues and helps verify the weight versus the intended weight, possibly of the real-world equivalent of the model. You want to run this in solution 101. There's no applicable cards. You can apply the loads, the acceleration loads in Patran, pass or fail. You want to see the resulting force in the direction of the inertial load to closely match the intended mass of the component or assembly, and you also don't want to see any abnormalities or such as unreasonably large displacements when viewing the model, the form shape of the model. And it is recommended that you apply each of the 1G loads in separate load cases so that you can easily verify that the resulting weight of the model is in the direction of the force, inertial load. And the FO6 file can easily be searched for the output force by searching for MPC force resultant, which shows the reaction forces of the model. The other runs you want to do are the enforced displacement runs. Essentially, you enforce a small displacement, for example, 1/1000th of an inch, in the X, Y, and Z directions, as well as rotations on a single node, and it will clearly show the analyst if your model is behaving as a rigid body. You want to run this in solution 101, and you want to apply displacements in Patran. The easiest way to verify that the model is behaving properly is to load the results into Patran and look at the displaced shape in the direction of the enforced displacement. So the model should appear as a single color when plotting displacements and the results for your fringe plots, and the max and min displacement should be the same as the applied displacement. So for example, if you apply displacement of 1/1000th of an inch, your entire model should be moving 1/1000th of an inch. So you want to apply this displacement at the same node as a fixed displacement. So you want to constrain all 6 degrees of freedom on a node, and then you want to apply a separate displacement where you apply the displacement in just the X direction, for example. If you look at your analysis deck that's written out by Patran, you'll see that Patran is creating a dummy force to actually solve the model for the enforced displacement. And it is recommended that you apply each of these displacement loads in a separate load case for easy verification. So, excessive pivot ratios is calculated, or the max factor to diagonal ratio is calculated in solution 101 by default. So it will be outputted in the FO6 for both the 1G inertial loads and the enforced displacements that you apply. And an improperly built model will encounter excessive pivot ratio warnings in the FO6 due to ill conditioning of the global stiffness matrix. There are no cards that are required. Patran calculates this by default. 2 cards to use cautiously are param bailout and param max ratio. If the model fails, you can search for fatal, and you'll see an output of where the model is having issues. It tells you at specific grid points, and you can track down these issues. So if your model does terminate due to excessive pivot ratio warnings, you can either loosen the max ratio default tolerance from 1e to 7, or you can use mechanisms using param bailout -1. So if you are going to use these cards to debug your model, you should be careful to ensure that you remove them from the analysis deck and that you don't continue solving the model in the future with these cards in. Some possible reasons for error. If you have a grid point that's failing in degrees of freedom that don't belong to the element type, you probably have degrees of freedom mismatch between elements. So for example, if you try to connect a beam and a solid together, you might see that solid node that's being shared failing degrees of freedom 4, 5, or 6. A node that's failing in all 6 degrees of freedom could possibly be constrained or hanging. If the value of the pivot ratio warning is negative, the node is unconstrained in that direction, or if there's a stiffness issue. Some other possible causes are flexible elements next to very stiff elements or material properties, highly degenerate elements, or property values mismatched. For example, if you accidentally inputted the value for elastic modulus for Poisson's ratio. It also might be helpful and interesting to see the distribution of the diagonal ratios of your model, even if it doesn't fail due to excessive pivot ratios. And you can use the following card placed in the executive control to show that distribution. Once again, it's not necessary, but it's a nice check just to see the overall quality of your model. And also in Solution 101, epsilon, or round off, is also automatically calculated by the solver. And it is the result of the work done, normalized by the strain energy of the model, and is an indication of the round off error in the model. Like I said, it's Solution 101, and you don't have to input any cards into Nastran. It's calculated by default. The minimum allowable value is dependent on the analyst and company requirements. MSC has recommended an epsilon value of 1e to 9, though it should be smaller for small models or individual components. You wouldn't expect an extremely large model to have the same epsilon value as a single component within that assembly. Other notes, a small value of epsilon alone is not an indicator of a well-constructed model, and the value of epsilon can be found by searching the FO6 for epsilon. So that's all we had for you guys. Just a few recommendations here. For large models, it is recommended that checks be performed as you go, either as you are assembling the model or on individual components. It makes things a lot easier when debugging, especially with extremely large models. The checks and results should be documented so that you can prove to anyone in the future that this is a mathematically accurate model and that the checks were already performed. It increases the level of trust in whoever is reviewing your work. If you have any questions and requests for the presentation, you can email them to Paul Davis. His email is listed below, and I'll keep this up so that people can write that down. At this time,
might as well jump in here. Do you still have the using text pad on the following one?
Sure. So earlier I had mentioned a useful method for tracking different things down in the FO6. In this example, I'm showing how to find either failing elements or find where warnings have been issued by the solver, which are the 4+ signs. So this is just a useful way. Say you already ran the model and it takes 5 hours to run. You don't want to resolve it just so that you can change the geom check parameters to find only warning or failing elements. We'll provide this presentation to anyone that sends Paul an email, just because there's so many steps, but just a quick demonstration here. Essentially, you can use TextPad. I would believe other editors have similar functionality to TextPad here as I use here. But in this example, we're searching for elements that have warnings with those 4 plus signs. You then bookmark those plus signs and then select only those element ID numbers. You can then quickly reformat those element ID numbers, and then bring that into Patran and highlight those elements. So you can quickly go from that list of failing elements in Nastran back into Patran, and you can easily see where you're having issues with your elements. I've also used this pretty effectively for looking for other results, and it saves a lot of time rather than scanning in manually through the FO6. Back to that and take any questions if anyone has any. Is anyone out there?
No, nobody out here.
That
was John.
It was a nice presentation, Austin.
Yeah, good job.
All right.
Well, if we have no questions, I think that's it.
You guys said you're gonna have you're gonna provide this presentation.
Yeah, just send me an email. So
what's your name? Paul what?
Yeah. Got that up there. I'll fire it. We'll clean it up and fire it out to anybody that wants it. And
cool.
This is actually something useful to keep and build off of, especially, for somebody that's starting out with the MSC products, because digging through the documentation can be having a place to start is really helpful, and you can build off of that and just add things you need or specific for your particular company as you go along and come up with a nice traveler on how to proceed through an analysis. And if everybody's doing things the same way, it makes it much easier handing off a job from analyst to analyst if everybody's following through the same types of procedures. And it makes it easier packaging things up and handing off to a client too, because we can normally have everything they're requesting, but if we do get special client requests after that, we can actually add it to the traveler and have a nice package to deliver at the end of the job.
It's a nice automated piece of information. Thank you.
Thank you, Pat. Okay.
And I believe next month we're going to have a seminar on Apex.
Yeah. So this seminar here leads up to a new product that MSC is releasing called Apex, and next month we'll be having a seminar on that, which will be less wordy and referencey than this presentation, and more of a nice little taking a real world model that's not overly complex, and basically showing you generally how you get something in from a client in a parasolid and quickly taking it to something the analyst can work with. So it should be pretty interesting. You'll like it, Pat and John, and whoever else is out there. So and we'll send those out.
Can you repeat the contact information to get a copy of this presentation for those who aren't able to see it?
It should be right up on the screen right now, my email address.
I'm not. The join me wasn't working. I'm not able to see it.
Oh, okay. It's paul.davis, so Paul.Davis, at esacorp.com.
Perfect. Thank you.
Thank you.
Well, that's it. Okay. Thank you all for joining us, and hopefully we'll see you in November for the Apex seminar.
All right. Thank you, Paul.
Thank you.